We're about to move to 2D systems. For 1D systems, we've seen two main examples. We've seen flow on the real line, and we've seen flow on the unit circle. Here our variable might represent population or position, and here our variable representing phase. For a 1D model to be useful, we need a system where it's okay for the state of the system to be described by one variable. So in this case, the state of our system was x of t, and in this case, the state of our system was theta of t. What if we wanted to represent interactions? Well, we weren't really able to. Specifically, when we were talking about the oscillators, it would have been nice to look at how multiple responsive oscillators interacted, but we were working in 1D, so we couldn't do that. Thinking about X in terms of modeling a population, it would be nice to know how two different populations interact, or maybe how harvesting might have its own evolution in response to population. We might want to have multiple chemical reactants in a chemical reaction. We might want to be able to have not just a time-evolving position, which is what we have here, but also a time-evolving velocity. So those are all examples that we can't represent using a 1D first-order system. What happens in 2D? We're still going to have fixed points, we're still going to have bifurcations, and the new phenomena that we're going to encounter there is that it's also going to be possible to have oscillation without using phase variables. So it might be possible to have oscillation in an interaction between two populations where the long-term behavior of the populations is that both of them are oscillatory with time. What math are we going to need to work with systems with two variables? Well, in 1D, one thing that we did was found fixed points. It's not going to be a big deal to find fixed points in 2D. We're just going to need to find solutions to two equations at once. What about stability? Near a fixed point, we used a Taylor expansion, and we looked at what was happening to this first derivative. Specifically, we looked at the sign of this first derivative to understand the stability of the fixed point. Let lambda be this value. It's just a number. Well, when we move to 2D, we're actually going to be using eigenvalues here. And so we're going to need to recall eigenvalues and eigenvectors before we're ready to work with 2D systems.